Okay, well, let's get going. So today our topic is analyzing time to event data. And so I'll start out by the basics of time to event, or in medicine it's called survival analysis. Then we'll look at probably the most used method of survival analysis, Cox proportional hazard regression. And then we're going to talk about a couple of topics that are not often looked at in the literature, but they probably really need to be, and that's multiple events and the idea of competing risk. And then I'll end up with talking about or summarizing our regression models that we've talked about. So time to event analysis, or in medicine, it's usually called survival analysis. In manufacturing or industry, it's called failure time analysis. And so in this analysis, we have two outcomes. We have an event, which is dichotomous, dead, alive, positive, negative, whatever it might be, and then the time to the event. Now, sometimes the event is maybe what we call a composite event. And this is often done because if you look at just one of the events, there aren't too many of them. So and sample size and power for a randomized trial is usually dependent on how many events there are. So, for example, we might have a composite event of non-fatal myocardial infarction or non-fatal stroke or cardiovascular death. So in that case, if a patient has any one of those, they have the event. If they don't have any of those, then they are event-free, I guess you would say. And so we have to have the time factor in our analysis, and that means that we need a beginning time and an ending time, or a start-stop variable. And in survival analysis, we're going to account for censoring. I'll talk about that in just a minute here, where the exact survival time is not known. And then, of course, if we have a comparative study where we want to look at two treatments or several groups, we can then compare the survival functions to see if there's a statistically significant difference. But we might also want to assess the impact of different covariates on the survival function, like demographic, age, gender, so on, or clinical variables, diabetes, previous heart failure or something like that. So censoring occurs when a subject is observed for some period of time without the event of interest, whether it's death or recurrence or whatever it might be, occurring. And the assumption that is made in the analysis is that the censoring process is independent of the failure process. And most of the time in the literature, what you'll see is right censoring. And so a person or a patient can be right censored if they're lost to follow-up before the end of the study or before the event occurs. They might withdraw from the study, or the study comes to an end and the person has not experienced the event. And then we'll talk about this at length later on. Death could be right-centered if the particular event we're looking at is something other than death. Okay, so here's a picture of right censoring. And so here we have 11 patients we have a trial that's, say, lasts 2 years. And so we have 3 patients that enter right at the start. The top 3 patients enter right at the start of the study. And the symbols here indicate censoring, or the star indicates they experienced the event, whatever that might be. And so here's a person who entered at the beginning, and then maybe about, say, 6 months or so into the study, they experienced the event. Whereas this person came to the end of the study, didn't experience the event, so we would call them censored. And here's a person that is censored close to the middle of the study, but didn't experience the event, and so they might have been lost to follow up. Maybe they just, dropped out, or somehow they lost track of them. And then the same interpretation for the rest of the patients that we have indicated here. And so we see that patient number 10, we can see that the trial ended, and then they experienced the event after the trial ended. So this event would not count in our analysis, because our time is from time 0 here out to, say, 2 years or whatever. And so at the end of the trial, or when the trial is terminated, if the event hasn't occurred, then they're regarded as censored. And so when we analyze the data, what we do is something like this picture here, where the entry time is set to 0 for all patients. And then from time 0 to whatever time they're in the study, either censored, dropping out, or they experience the event. And we code the event 1 if it occurs, and if they have no event, then it's coded 0, and that's what we call our censoring variable. There's a couple of other types of censoring that are less often seen in the literature. In fact, it's kind of rare to see them, but one is what we call interval censored. And so the event is known to have occurred in an interval of time, but the exact time is unknown. And so that's represented by patient 2 there, where they have the event in some interval of time. We don't know the exact time. And then the other type is what's called left censored, that is even less common in the literature, where what you're uncertain of is the beginning of their at-risk time. And so patient 1 here is left censored, and even though we know when the event occurred, we don't know when their beginning time started. We observe them at some particular point, but we don't know. For example, date of diagnosis might be a common one for being left censored. That is, we know when and if the patient had the event, but we don't know when. If we're looking at time from diagnosis to time to event, we don't know the time of diagnosis. And so there's different ways of handling these 2 other censoring types here. But as I say, most often you'll see the right censored data in the literature. So our survival function, S sub t, is defined as the probability of surviving longer than time t. And so S sub t is equal to the probability of surviving longer than time t, so that capital T there is greater than little t. We can also define what's called the hazard function. And the hazard function is the probability of the event occurring at time t, or that's also known as the instantaneous failure rate. And usually, if we present this, it's plotted as the cumulative hazard function, the accumulated hazard until time t. Now, as you can see that the survival function is part of the equation here. And so if we know one, we can calculate the other. And as I mentioned, the survivor function defines the probability of surviving longer than time t, and the hazard function is the derivative of the survivor function over time t. And so, as I said, if you know one, you can find the other. But that's the difference we want to draw here, is that survivor is surviving longer than time t. Hazard function is the dying or experiencing the event at time t. So here's give you an example of how this is calculated. And so this is the Kaplan-Meier survival function. So we're not going to look at any other factors here, just whether patients were censored or whether they died. And so we start out at time 0 here. And in our database here, we have 74 patients. And so at time 0, no one has died and no one is censored. So our probability of survival at time 0 is 1, and our cumulative survival rate is 1. So now at time 7 here, 7 months, we'll say, for example, we still have 74 patients at risk, but at this particular time, 1 patient dies and no one is censored. So now the probability of survival then is 1 minus the number of deaths in this case divided by the number at risk. So this 0.9865 is 1 minus 1 over 74. And so to get the cumulative survival function, we just multiply the 0.965 times the previous cumulative survival rate, which is 1. So that's just 0.9865 again. So then if we go to the next time, say 11 months, now we have 73 patients at risk because we lost 1 here. And we have another patient that dies that no one is censored. And so now our probability of death is 1 minus 1 over 73 now, because there's only 73 at risk. And so now this is 0.9863. And then if we want the cumulative hazard, we just multiply our probability of death in this interval by the previous cumulative probability of survival. And so we get 0.9865 times 0.9863, and we get 0.973. And so this continues down then. So like in the next time period at 12 months, now we only have 72 patients at risk. We have 1 more death. So here's the probability of death. We multiply that by the previous cumulative probability of survival. And so we get 0.97 times 0.986, and we get 0.9595. And then this is the way that it proceeds all the way to the end of our study, where we have at 3 years, there's 56 patients at risk. Nobody dies at 3 years, but all of the remaining 56 are censored. So the probability of death is 1. Multiplying that by the previous cumulative rate, we get our cumulative survival rate at 3 years as almost 0.8. And so if we plot this, it might look something like this. So in this case, I've had data where we looked at patients that had chest radiation and patients that had no chest radiation. And so we can see that the cumulative survival functions here are pretty similar. And it turns out they're not, even though the chest radiation has a smaller survival function over time than the no chest radiation. They're not statistically significantly different. You can see from the numbers here that we do have something of a issue with this analysis, and that there's a huge imbalance between the number of patients in each group, which could be a problem. But if we just look at this the survival functions here, what we can conclude is that the hazard rates over time are the same. And we can tell that when we have plots where the survival curves don't overlap, or not overlap, but are basically parallel. In other words, one survival function doesn't cross or connect with the other. So here, though, is an example where we don't have proportional hazards. And so we have 3 treatment groups here in older patients. A treatment group on warfarin, treatment group on aspirin, and then another treatment group with no treatment. And so you can see that we have non-parallel lines regarding aspirin and no treatment, whereas the aspirin group does worse for a while, but then the survival function crosses the no treatment. And so the no treatment group ends up being having the worst survival function. And so that's basically how you can tell, or an easy way to tell whether survival functions are proportional or not, is just by plotting the Kaplan-Meier curves and seeing whether they're parallel or whether they cross over one another. Then here's an example of plotting the hazard rate, in this case, the cumulative hazard rate, rather than the survival rate. And so these will be functions that are increasing over time rather than decreasing, because it's calculating the number, the cumulative number of deaths over time. And so we can see that in this case, the treatment of naproxen is favorable to the other treatment because the cumulative hazard rate is smaller over time than the rofecoxib treatment. So in statistical comparison of survival functions, if the hazards are proportional, then we can use what's called the log rank test. But that assumes that the survival curves are essentially parallel. 2 other tests that we can use that you might see in the literature that are used when we have non-proportional hazards, as the Wilcoxon test and the Fleming-Harrington test. And so basically these are weighted. And so the Wilcoxon places greater weights on events close to time 0, where the Fleming-Harrington has a weighting scheme for events nearer time 0, but different weighting schemes for events later in time. So just as we could do in linear regression and binomial logistic regression, we can do multivariable survival analysis. If we're interested in covariates that might affect survival. So, for example, a history of smoking or hyperlipidemia, diabetes, and so on. And so the most often used analysis for this is the Cox proportional hazard model. And basically here the survival function, where the bolded X is the matrix of your covariates, and that's equal to the baseline survival function raised to the exponent of the, as you can see, the essentially regression equation, where we have different covariates and their regression coefficients, the betas. So in this analysis, the covariates can handle both continuous and categorical predictor variables. And it turns out that we don't really need to know the baseline hazard rate. We can still calculate coefficients for each covariate and therefore the hazard ratio. But it does assume a proportional hazard, the proportional hazards assumption that, in other words, if you have different treatments or whatever, the survival functions need to be essentially parallel, that is, not crossing one another. Now, if they do, we can compensate for that, or we can look at that if we introduce interaction terms into our analysis, or maybe do stratified analysis. For example, let's say age, for example, affects our survival function, but the part that age plays is different for men and women. And so we might want to look at an interaction between age and gender to compensate for non-proportional hazards. So the hazard ratio then that we get from our equation is a measure of how often a particular event happens in one group compared to how often it happens in the other group over time. And similar to our regression slope or our odds ratio, it's basically a change in hazard rate for every 1 unit change if the covariate is continuous, and has a interpretation similar to that for dichotomous or categorical variables as it does for odds ratios. And just as an odds ratio equal 1 means there's no difference, a hazard ratio of 1 means there's no difference in hazard rates between two groups. If our hazard ratio is greater than 1, then that's going to indicate, unless it's not statistically significant, significantly different from 1, then that survival was better in one group or the other. So here's an example of hazard ratios where we have used an interaction where it turns out that the proportional hazard assumption was not met. And so in particular, we have an interaction between gender and race. And so you can see that the hazard ratio for males just alone by itself is 0.75, meaning that males have a better survival function than females, and that's statistically significant for African Americans compared to whites. Then it has a hazard ratio of essentially 1, is not statistically significant. However, if we look at the interaction between males and African Americans, then we see that we have a statistically significant interaction. And then we have a whole bunch of other variables in the model that are statistically significant. but the one that we would need to focus on is the interaction, because those are the variables that are causing our hazards to be non-proportional. And so as I mentioned, the hazard ratio is interpreted similar to the odds ratio. So for example, age, which we've looked at in 10-year increments here of 1.28. So that means that for every increase of 10 years age in patients, the hazard of experiencing the event increases by 28%. And then if it's less than 1, so for example, like with BMI, we have about for every 5 units of BMI increase, we have a decrease in the hazard ratio of about 8%. And so if we plot these, in this case, what I've done is I've plotted the cumulative hazard rates, and I've smoothed them. And so we can see here the interaction between gender and race. And so the hazard ratio here with the blue line is white males, and compared to the black males at the top line here is very different. And so that's why we're getting the interaction. Whereas females, regardless of whether they're black or white, are pretty similar. Okay, so that's kind of the sort of the basics and ins and outs of survival analysis. So now I want to talk about the case where we have multiple events. And often you'll see that the primary analysis, if we have a situation where multiple events can occur, obviously non-fatal events, they only consider the time to the first event. But if they don't look at multiple events, then you get kind of a not entirely accurate idea of survival. And often what they do is secondary analyses of the where they consider multiple events, and then often they don't consider the multiple events at all. So there's different methods for multiple event analysis. One of them, one that's often used, that you'll see a lot, is the Anderson-Gill method. However, this method assumes that all the events are independent, which, if you kind of think about it, that's probably not the usual case. If you have a non-fatal MI at one point in time, then that probably is going to increase your probability for a second non-fatal MI, or even a fatal MI at a later time. The two that are often used are the way when Weisfeld and the Prentice-Williams-Peterson methods, where the risk is conditional. That is, it might or subsequent events are probably correlated with earlier previous events. And so for multiple event analysis, those are the two that we often use. And so I want to go through an example from our hypertrophic cardiomyopathy registry. And we're going to look at the outcome of atrial fibrillation. That was one of the secondary outcomes we wanted to look at. The main one that we're still going to analyze in the future is sudden cardiac death. But obviously, some patients might have multiple atrial fibrillation events. So we're going to take that into account and look at multiple event analysis. And so in our data set, there were 127 AFib events among 96 patients. And so we had a number of potential predictors we want to look at: demographic, age, sex, and so on, clinical histories. And we had data on morphology, gene mutation. And then we had imaging data and biomarker data. So in looking at a model of predicting AFib, this is how we would set up the data when we wanted to look at multiple events. And so give an example here. So patient number one, and when we have multiple events, for each patient, we have an entry point and an exit point. So here, the entry point is always going to be 0 for their first time. And then the exit is if they are censored, or we come to the end of the study, or they drop out, or we lose track of them. So for example, patient one exited the study at 36 months. They did not have an AFib event. So that's coded 0. And then I've got a couple of covariates here, age and left atrial volume, that we're going to look at, but I just put them in here to see, or to show how this is set up in the data. And so patient number 2 here, their entry point is 0. At 14 months, they had an AFib event. So they're still in the study. So when they have if they have another event, then our entry point is whatever the exit point was here. And then the 37 here is 37 months, they had a second AFib event. So this person, patient number 2, had 2 events. But you can see that these covariates, because age here, although age is the age at start of the study, so that doesn't change. In reality, it could change, but in this analysis, we just use their age at baseline. And so then patient 3, who has 4 events here, you can see their entry and exit times, and each AFib event is indicated just simply numbered 1, 2, 3, 4. So that's how we need to set up the data. And we have, instead of our data being just one event here, AFib yes or no, we can have more than one event. And so we end up numbering those sequentially in time in the data set. And so here are some graphs that we plotted looking at the observed and predicted multiple event atrial fibrillation-free functions. And so I plotted for 4 different variables that entered into the prediction of AFib. And this is to see how well the observed and the predicted agree, and so that we can see for all of these different variables that the agreement between the observed and the predicted, the dotted lines, is pretty good. Obviously not perfect, but generally for all of them, it's pretty good. And so, for example, in the dyspnea, those that had dyspnea obviously have a worse survival function than those who didn't. On the other hand, you can see that for contractile percent here, the higher the number, the better the survival. Whereas with low contractile percent, we have a worse survival function than we do for the other cutoffs that we've used here. and then the same for LA volume and BMI. So that's using the analyses for multiple events. And we also did the analysis for time to first event, but as I say, I'm not particularly a fan of just doing that if you have multiple events, because it doesn't really give you a sense of survival related to all the events. Okay, then the last topic that I want to cover in some detail here is what we call competing risks. And so this is this situation where we might have multiple different events. And it turns out that if we have a competing event, that modifies the estimation of survival function of the event of interest. So for example, if we, in our HCMR data that we just looked at, death is a competing risk for AFib, or AFib was our event of interest, but if a person dies before they have an AFib event, then it turns out we don't get the correct survival function for AFib. Or in the example of chronic kidney disease, if your outcome is looking at time to dialysis, then death would also be a competing risk. So a diagram it this way. So if everyone starts out in the initial state with no event, then we have three different survival functions that we can look at here. A person might have an AFib event, and they might not have any other AFib events, or maybe they have multiple AFib events. We could extend this out here. Or they might experience death after their AFib. Or they might die before their AFib event. And so we call this multi-state analysis, but I'll give a better example here. So there's different methods for taking into account competing risks. And the most used one is the fine and gray method, where subdistribution hazard functions are created for each different event besides the main event. The problem with the fine and gray method, or the criticism of it, is that when it calculates the hazard over time, the hazard function over time, it has to include the competing event at each time, or at each calculation over time. And what that means is, so for your competing risk is death, that means that instead of a patient being excluded from the analysis if they died when the hazard function is computed further out in time, those that died previous are still included in that calculation. So some folks then think that, well, maybe a better way is just censoring at death, whatever the competing risk is. And so in the HCMR study, we did both. So we calculated the SHR stands for subdistribution hazard rate when we did Cox regression with competing risks. And then on the right-hand side, we did the Cox regression without competing risk. And for the variables, the covariates involved in there, you can see that there's very little difference between including the competing risks of the fine and gray method between just censoring at death. So the Cox regression without competing risk, we've just censored those who died at whatever time they died. Now, let me caution you, this may not always be the case. And this may be the case in our for our data because there were very few deaths. I think there were only 24 out of 2,700 or 2,600 patients. But anyway, you can see that regardless of the method we use here, that we get essentially the same estimates of the hazard ratios and their standard errors. So what I want to illustrate, though, is a better way of looking at competing risks. And this is to look at multi-state analysis, where we start out in initial state, and then we have an event of interest, and we have a competing event, or more than one competing event. And so what we're going to do is for each possibility here, compute a cause-specific hazard. And basically, this is a Markov model. And so here's an example, a little more complicated example. So we start out at in the initial state, and so we have two competing events here, 1 and 2, and then we have the event of interest. And in the statistical jargon, this is called the absorbing state, the event of interest. That's the final state. You can't go from that state to another state, with one exception. And so we see that a patient can go from the initial state to competing event 1. They may or may not stay there, but then they could also experience the event of interest. We might then go from competing event 1 to competing event 2, and then to the event of interest. And so we will compute a hazard function for each of those possibilities, as illustrated in our diagram here. Now, as I mentioned, in most contexts, you can't go from, if you experience the event of interest, then you can't go back to another event. However, in some contexts, that is possible, where you have what's called an illness recovery model. And so I've illustrated that by the dotted, or the dash, not the dotted, but the dash line in the diagram there, where you go back from competing event 1 to the initial state. And so that might be an example, might be where you are looking at infections in the ICU. And so you might get an infection. So you would go from the initial state to competing event 1. But then if you're in the ICU for a while, then maybe the infection gets taken care of. And so you go back to the initial state. But for the most part, once a patient experienced the event of interest, that's the end. So this is sort of the I guess the math of doing the Cox model and computing cause-specific hazards. And so basically, you can see at the bottom there that what we're doing is we're looking at the number of observed patients in an interval and how many transition to the next state, state J, at a particular time, divided by the number of persons at risk just prior to the next time. So that's, I don't need to go into detail there, but that's basically what is being calculated for each of the possibilities of competing events and the final event. So I'm going to use an example here a pretty old example, the Credo trial. This is back when clopidogrel was being looked at as a benefit for patients undergoing percutaneous coronary intervention. And so the trial, the randomized trial, randomized patients to clopidogrel plus aspirin or placebo plus aspirin. And in this case, our primary outcome was the composite of cardiovascular death, non-fatal MI, or non-fatal stroke. So again, if the patient experienced one of those, then that was the outcome of interest. So here are some of the demographics in the Credo database, and you can see that it was a randomized trial, so all of the potential confounders like age, race, and so on were pretty much similar in both groups. In the line that says death, MI, or stroke, so you can see that there's a significant difference there. So in terms of the differences in proportions. However, the different components of that CV, death, MI, or stroke are not statistically significant by themselves. When the article was published, this is the figure that they had, and so you can see that what they published was that the hazard function, the cumulative hazard function, so that the clopidogrel group is doing better over a 12-month period than the placebo group by an absolute value of 3%. Or if we express it in terms of the relative risk ratio, then 27%, and that was statistically significant. So if we look at this as a competing risk model where the competing events, instead of looking at it as a composite, we look at CV death as the primary interest, and we're going to look at non-fatal MI and non-fatal stroke as competing events. So if we do that and we use the typical fine and gray method, then this is the graph that we get, where the red is the placebo, the dark or black is clopidogrel. And then, although it might be difficult to see here because I should have used dots instead of dashes, but the short dashes for stroke, that's the two plots at the bottom. Death is the one right above that, the solid line, and then MI is the plots that are at the top there that have the higher incident, cumulative incident. So this would, if we did this, separate in this way, this is going to, we can see that MI is the event that's really driving the endpoint event of cardiovascular death. So here is our little diagram where I put in, like we saw before, where I put in the competing risks of MI and stroke, and cardiovascular death is our absorbing state. And so now we're going to calculate hazard functions for each path there. So we can see that patients can have it go from no event to an MI, then they might die after that. They might not. Same with stroke. Then it's also possible to have an MI and then later have a stroke, which some people did. And theoretically, at least, it would be possible to have a stroke and then an MI, but that didn't occur. That's why the line there is dotted, because there were no patients that had a stroke and then had an MI. So when we do it this way and then plot the multi-state transitions, we again see that MI is the primary driver of our hazard functions. And so that having an MI, the probability of death is much higher than it is if they have a stroke. So even though clopidogrel is doing better than the placebo in each case, that the big driver of cardiovascular death is having an MI. And so there are conclusions that we can make is that that MI drives the composite outcome results, and the greatest risk is the transition from myocardial infarction to cardiovascular death. And it turns out that transitions from MI to death, virtually all of them occurred within a few days following treatment. So that's why you get such a huge impact of myocardial infarction. Basically, the point that I want to make is that in competing risk, that multi-state analyses provide more information on the survival distribution of the events and their impact on each other. And so my recommendation to investigators who are doing this is to, rather than do a composite event, to do transitions, to do a look at the multi-state. However, I'll have to admit that I don't think any of them taken my advice to this point. But anyway, at least in my opinion, it's a lot better way of doing it. Okay, so let me then finish up by sort of going over assessing what we've looked at so far in our seminars. So we started out with looking at linear regression. And as far as the predictors are concerned, they could be of any type, categorical or continuous. The outcome, though, is continuous, and we assume that it's normally distributed. Then we looked at logistic regression, where the predictors, again, could be of any type, but our primary outcome, or our outcome was in binary logistic regression. It was either yes or no, a 0 or 1 kind of variable, although we did look at some where we could have categorical logistic regression. And then finally, today we looked at survival analysis, where we have actually 2 outcomes, a binary outcome, an event or no event, and the time to the event. And so in survival analysis, we have to take into account censoring. That is, if we lose patients to follow-up, we can take that time into account. And so in terms of the regression models, linear regression, we looked at the outcome as a function of alpha plus regression coefficients times the independent variable, or if we had multivariable linear regression, we'd have more independent variables. But basically, then we're looking at the rate of change. So the beta represents the increase in the outcome, y, in this case, for every unit increase in the independent variable x. When we looked at logistic regression, we looked at logit or the log odds. And so our regression equation is similar, except now when we have our regression coefficients, our betas, if we exponentiate those, we get the odds ratio. And then finally today we looked at survival analysis, where our result is our hazard ratio, or our survival function, however you want to express that, where the survival is the probability of surviving past a certain time point, where the hazard function is the probability of dying at that particular time. So a couple of things that I want to just point out. When we do modeling that predicts some particular outcome, remember that it's the combination of predictors, not whether individual predictors are statistically significant. And I've gotten this more than once in reviews that where we have a model and some of the actual predictors, when you calculate the confidence intervals and the p-values, they're not statistically significant, and reviewer will come back and say, well, why is this in the model? Well, the reason is if you take it out, then the model doesn't predict as well. So just, kind of remember that when you look at articles that have a model that predicts some particular outcome. And then also we need to do model evaluation. In linear regression, it was the R-squared we looked at. In logistic regression, it was discrimination as well as calibration, and that's the same sorts of things that we looked at, that we would look at in survival analysis, is how well does the model predict the observed. So I went to, and this is, you can do these analyses, all the ones that I've talked about, in major packages here, SAS, data, or R. And I have a number of references here on survival analysis. And I think the folks at Georgetown send the slides along to folks who have registered for this. So if you are interested in the references on survival analysis, there in the slide set here. So I want to thank you for your time. I will want to say that we will not have a seminar in December, but we will resume again in January. So I think I might have a minute or two left if there's any questions or any comments someone wants to make. If you do have questions or some particular point here of interest that interests you, you can email me at my MedStar account. So I will thank you for your time and participating. And as I mentioned, we will start again in January. Thank you again.